Oh, Bowden is online.
Yeah.
Happened to Bowden. Bowden, are you there?
Yeah, I'm here.
Hello?
Yeah, I can hear you.
We cannot hear you or see you.
Oh.
That's Christian.
Do you hear me now?
Hello?
Where does the volume play through? Because it looked like his video was getting highlighted.
Oh, I see. So you're saying it's our
It
side?
might not.
Hello, Bowden?
Yeah, can you hear me?
We cannot hear you. My mic is working, so you think it's our side.
I don't know. Does it usually just come through the computer?
Through this actually, right? Once it says came, I'm just going to log in and to just make sure that it is before I do anything. Curtis, can you hear us? That will be a confirmation.
Yeah.
Curtis, can you say something?
Hello?
Okay, so we are on the. Just. I can hear Curtis. Okay. Hello?
Hello?
Yeah, now we can hear you. But now it is this, correct? It's not going.
Yeah.
Let me disconnect and come back again. Okay.
Okay.
Or maybe I can do this. Speakers, headphones. Which one should I select? Display audio, maybe. Can you say something again, Bowden?
Hello? You can hear me?
Hello?
Hello?
Is there a volume button on that TV?
Oh, yeah. Sometimes we have that issue, right?
Okay.
Yes. It's pretty high. Okay, disconnect again. Hello?
Hello?
Yeah, okay. So I can hear you on the computer. So I'm going to log out and log in. I think that might help. Okay.
Okay.
Assign and leave. So Bowden, you're going to be the host for 2 minutes. Hello?
Hello?
Can you say something, Bowden?
Hello?
Yes,
Can you
he's
hear me?
saying something. I cannot hear him. Okay. Hello?
Hello?
Try again, Bowden.
Oh. Hello? Hello?
Hello again.
Hello?
Yeah, I think we can manage with this. Yeah. We can hear you only on the computer, not on the classroom TV.
Okay.
I think it should be okay. It's not that bad. Hopefully it doesn't persist. So we have a midterm 3 on the 6th. which is Friday. And this is going to be take home, completely take home. Right, that means to say that it will be uploaded sometime before Friday. So maybe even today, depends on how much I finish preparing the exam. And it will be due on Monday, the next class. So you have sufficient time to look into stuff. But that also means that grading will be a little different from the way typically I grade midterm exams. And if it's an in-class exam, I'm very lenient, like because you have had nothing to refer to. So it's different. Here I expect you to refer, even internet, everything is allowed. But then I expect you to at least learn. I'll check for the correctness in more detail. So that's the point. This is one of the reasons why I want to do this more than, even though I had decided that before, is that the homework 10, most of you did not do very well. Like, so I think you did not get the point, even though the concept was relatively easy. It is a point charge concept. So the exam will be based on homework 10 and homework 11. Even though homework 9 is also supposed to be part of it, but the exam will be completely based on homework 10 and 11. Especially, I give you the questions that's supposed to be needed for like more than the typical 3 questions. I give you more than that. But since I'll be giving you questions, I don't have to tell you that you have to prepare the whole thing, but it will be based on that also. So if you really want to be prepared. But I'll be giving you enough time so you don't really have to. Homework 11, you don't have to worry about the problem 3, like except problem 3. Except. It is more detailed. I don't think I want you guys to go over it and spend a lot of time. So what I decided today is that I'll roughly go over the homework 10, at least the concept wise, and tell you what exactly is expected. So this is method of images. We're typically talking about point charges. So think of a planar surface. So this is a conductor. And you place a positive charge in front of it. And you would ask, what happens to this positive charge? Does it experience a force or not? And it turns out it does experience a force. Why does it experience a force? This is a perfect conductor, so it will actually pull in a lot of positive, negative charges on it. And its distribution is more here and less on that side. And then we have actually calculated what is its charge distribution of this negative charge, and this negative charge is actually pull the positive charge. But we don't have to do that. It's much simpler than that. It is, instead of doing this problem, if once you realize that this is A, just for reference, this is only for reference, there is no conductor here. Just for reference, have a line which represents a conductor, but for all calculations, we don't have that conductor. Again, place a positive charge, exactly the same distance A. But now all the physics of this is governed by an image charge, which is exactly distance A and opposite in sign on the other side. So that's your Q plus Q, and that's your minus Q. Everything is governed by this. Typically, what are the questions you can ask? What is the force on this charge? What is the energy of this configuration? Energy means this positive charge and this conducting plate interact with each other. So there's an energy associated with it. What is the energy? What is the force? That's something you can ask. We can also ask, what is the charge distribution here? That's a harder thing. Right? How much is the charge distribution here? That's a harder concept. But anything else, it's easier. If it is force or potential at any point, we know 2-point charges. That's like introductory physics, 2-point charges. I can ask you the problem 1 in the homework 10 asked you what is the, so if this was A, there is a point A here, and there is a point here. What's the electric field associated with it? There is an electric field due to the positive charge here. So that's your electric field due to E plus, let's say. And this negative charge will have an electric field pointing towards it, which will be weaker because it is farther, something like this. So that's your E negative. E plus, or in general, remember, electric field due to a charge at R prime is equal to 1 over 4 pi epsilon naught. Vector R minus R prime, wherever the source is, this is source, this is the position of point charge. Position of point charge. And this is observation point. Observation point. In this case, this is the point of observation. This is the place where the source is. And divided by the magnitude of this whole quantity. And this, many of you got it right. So first you have to do this for this positive charge. You have to do this for this point charge, and then vectorially add it up. And it was given that this is distance A, that's distance A, that makes it A plus A plus A, that's 3 times A, and then A. And most of you got this correct. So the electric field, total electric field, is E plus plus E minus. Right? As a vector addition, you add these two quantities. We can also find the electric potential at that point, right? Electric potential is easier. Electric potential, I total, will be equal to phi plus phi minus. Right? That's the electric potential due to the point charge. So that's 1 over 4 pi epsilon naught. And then Q over R minus R prime. And you have minus 1 over 4 pi epsilon naught. This is minus Q. And this is R, let me say this is the positive charge, right? It's R minus. I'm specifically not doing this, but you can calculate the distance between them, right? If this is A, for example, R minus R prime plus, this will be equal to, that's your positive, that's your R, so that's A square plus A square, square root of that. Same thing with R minus R prime at the negative or the image charge position. This is A plus A plus A, 3 times A square, plus the height is still A square, and that's this. So that's square root of 2A, and this will be 9 plus 1, 10, square root of 10A. And once you substitute that in, and then you simplify things here. Even though this is done for a single positive charge, this works for any number of positive charges. You can immediately generalize this. So, for example, if you had a conductor and 2 positive charges in front, again, replace the conductor with a mirror kind of situation, but it doesn't exist as far as your analysis goes. So you could have a positive charge here. So let's say that's Q1. And there could be a negative charge, not necessarily the same distance. It could be anywhere. It could even be not in the same plane either. So that's your negative charge. So let's say Q2. Or it could be positive itself. again, the whole system boils down to finding the image, right? So it is immediately you say there is a negative charge in here, which is negative Q1, and there is a positive charge in here. So that's your a positive Q2. So let's say this is, yeah, Q1 and Q2 are, let's say, magnitude positive quantities. And we can forget this whole situation. Now, there are various questions one can ask. What is the force on Q1? And if you're asking for the force on Q1, there is a force from 2, there's a force from image of 2, and there's a force from Q1. So there are 3 forces you have to add to. So that's one question I can ask. You can also ask, what is the force on the conductor? The force on the conductor, remember, is equivalent to Q1 and Q2. Q1 and Q2 together form the conductor. So for all practical purposes, our conductor is equivalent to the combination of image of Q1 plus image of Q2. For that matter, all the images, right? That could be a bunch of images. And again, one can ask, is there a torque on this? One has to find all the forces and take a reference point and calculate the torque. And whenever we say, is there a torque on the conductor, we are pretending find the torque on Q1, find the torque on Q2, and add them up. This together, the system is what it is doing. Any questions at this stage? You can also do energy anywhere. So this is point charges, like all the physics that we did before comes into picture in here. And in that sense, it is easier for me to ask questions because I can ask any of the questions that you're expected to have mastered a lot in your introductory physics course. Any questions again, Gordon and Curtis?
No, I'm good.
So far, no.
Okay, so that's all good. But now there was a small leap we took in the problems, and that is, and before we do that, let me do a similar problem which was not in the homework, and that's the following, which was actually showed up in the new homework or the one that was submitted today. So let's say instead of one conductor, we have 2 conductors. Like in your previous homework, it was making an angle, but now let's say they are parallel. Probably many of you have thought about this, even in movies and videos, they try to highlight the complication involved in this or the cool feature associated with it. If you're sat in the old traditional barber shops, you have two mirrors, one behind the other, then you see this feature. So this should be thought of as 2 mirrors, right? But now let's keep a charge in here. Let's not keep it at the center because just to avoid the simplicity associated with it. So let's have a positive charge. So I'm just going to, so dot is going to be a positive charge. That's positive, and cross is going to be negative. So let's have that notation. Now, this is infinite. There's only one positive charge. I can immediately make this more than 1 charges, but now we have to find the image, right? So you start with the first plate, and surely there's an image. That's the image in there. But then we ask, okay, what next? I can also say that, oh, this will also form an image there. So let's say this is going to have an image here. So this is the image due to the mirror on the right. There is the conductor on the right, conductor on the left has an image like this. That's good enough, but the point is that the conductor itself makes an image on the side. So this is the image of the conductor itself. So this is, let's call it right, and this is left. Right? So this is the image of L due to R. The image of L on R. Once you have that image, then this can now reflect across that. So that's this point, and you have again this can now reflect around this, and you can immediately get a whole series of them, and that's how your images are found. And actually, if you've gone to museums, you might have seen there are these walls when you make an angle at the walls, and you have mirrors, and use how many images do you see? Right, that's a standard exploratory system you consider, or you can ask the question: if you take two mirrors and keep them at an angle, how many images will you see of yourself? Is that clear, the question? Maybe an extra credit problem? Yeah? Extra credit? So if I were to have two mirrors, this represents a mirror making an angle, and you stand here in between. Right? That's your face, like the smiley, right? And how many images will you see of yourself in that? Like often in a museum, you see the science museums have, since this is very easy to build, it's not very expensive, that's very standard. Have you guys seen it? If not, take two mirrors and keep it at the corner of the wall, and
So it's two mirrors at 90 degrees.
yeah, let's keep it 90 degrees. How about that? Let's make it simple.
Okay, yeah, I think I know what you're talking about.
And so if it is 90 degrees, how many images will you see? How about that? So you're standing here, right? How many images of yourself will you see? You'll surely see an image here. Agreed? Due to this mirror. And on this mirror also you will see. That shouldn't be hard to decipher. But is that all that you see? That's fine.
If they're perpendicular to each other, that would be it, right? Or no?
Actually, no. You will see one more. If it is perpendicular, you will see one more here. How do you justify that? You will see an image here. How do you justify that? Use your optics.
Like superposition? Is that?
Yeah, so let me do that just so that I convince you guys on this. Because we're using method of images. So let's see. It's usually tricky to do it, but if you follow the rules, if you use the geometry correctly, it comes out. Okay. So that's your, remember how does optics work, right? How does our eye work, right? Our eye means or interprets, this is our brain interprets, if there are two rays of light coming in. So if there are two rays of light coming in from a point, so think of this as a source. That is light source, right? An electric bulb or a candle. And from evolution or whatever the reason, we have learned, our brain has learned that when two rays, and there are many rays of light coming in, but typically just two is sufficient, and this is our eye. So this is a huge magnified eye. Okay? That's your eye. And that's your pupil of your eye, and that is brain inside. Now, our brain is smart enough to sense this angle. But it cannot, of course, measure this angle. It only sees two rays of light coming in, and rest of it is projection. Like our brain is smart enough to extrapolate this line backward, and wherever it meets, our eye assumes there is an image. Okay, now look at our, this is a mirror now. And let's say this is a wall. Right? That's a wall. And there is an eye here. And this is an object, this is a source of light. And let's say rays of light. So this is a source of light, that's a candle. 2 rays of light go in like this. Actually, many rays go like it, but we need only 2 rays of light. Like, is that clear? Many rays, but for our argument, we just need 2 rays of light. Law of reflection tells us that this angle has to be the same. So this light will reflect like this. This angle has to be the same as this angle. And law of reflection, and for this ray tells us that it has to be like this. Okay? And let us say there is someone else standing here. So that's your eye, a magnified eye. Huge eye. But I can make that smaller by picking to the cone of this rays. If I make it smaller, then I don't need that such a big eye, right? And this could be me standing here. My brain is not smart enough to realize that there is a mirror there. It only can sense till here, right? My eyes, I can only see till here. I cannot sense what is outside. So this is your rays of light, but it is smart enough that, or this time it is not smart, it is sort of foolish in the sense that it doesn't realize there is a mirror. It will project it backward. Like this is in our head going on. Like we don't really do this, but our head does this. It goes backward, and wherever it meets, it says that there is an image. My brain interprets that there is a source there. That source, because it doesn't exist there, that's called an image. Often there is a real source there. But if it is not there, if the source really isn't there at the place where it's supposed to be, then you call it an image. And then there is a concept of virtual image and real image, but let's not go in there. Yeah, extra credit, right? What is virtual image? What is extra real image? Extra credit for your optics. What's the difference between a virtual image and a real image? So will this be a virtual image or a real image? Maybe I already said it.
I would assume virtual.
Yeah, this will be a virtual image in the sense wherever you, so I can say that what's the difference between them. If the light actually goes through the point where the image is, physically goes through. Here physically it is not going through. The light actually is going from somewhere here. If it doesn't go through, then it is a virtual image. But sometimes there are images where actually light does cross through that point, even though there is no image formed. For example, when you have a projector and you see an image on the screen, so the light is actually touching that screen. Right? So that's a real image. So if you were to move the sheet of paper, light will just cross through. So light intersects at that point and goes through. It's like saying if this was real, it will just cross through. If you keep a paper off, there is an image formed. So in that sense, that's a real image. So now we have to do, so there is a source, let's say somewhere here. And we want to do the same idea, this one with this. So this is one of the mirrors. And that's the second mirror. So let's first get the two. We're going to use that principle. That's one of the rays. That's second ray. Correct. And it reflects again like this. And we cheat in a sense. Right. So that's here. That's one of the image where it comes up. That's your image one, let's say. I can have the same thing here. There will be an image formed there. Right? So again, this is your ray of light, and it reflects back. So that's here, and the second ray of light goes like that. And that's the second image. You move your head or your eyes, you get an image there. Something like that. So that's your image 2. But the claim is that there is one more image here. How do you justify that? Right. So if you now notice, so I want an image there, right? So let's have a light coming from here. Notice all this happened in a single reflection. This is now, since there is a reflection, this will get reached here, and then it will reflect this. And now have a similar arrangement with the next ray. If that makes sense. I mean, if you do this with a correct ruler, it comes out much better. But even a small error in your angles will make this very hard to do. So that's your third image. Is that clear? Convincing? Okay, this is the third type, if you want. You could easily say, oh, can I have more rays coming in? But since it is perpendicular, the best I can have is only 2 reflections. And after the second reflection, it will diverge off. It will never be, you will never be able to get the second one onto this. But if the angles are different, you can. Then you can get multiple reflections. Right? But, Christian? One thing you notice that this 1 and 2 were formed out of single reflection. The third one was formed out of 2 reflections, so it will be weaker. That means to say it will be less brighter. If the reflecting surface is not a very good reflector, then it will be harder for you to see the third one. But that's the idea of getting images. So let's go back here. Let's do the simpler version, and I'll come back to this very soon. Because that's one of the ones I want to highlight. That was part of the homework. Right? Any questions on that?
I'm good.
Okay. Okay, so let's get back to this. Now, oh, maybe I should go back here. Sorry. Notice that even though I used all this ray diagram to get this, how could I have got this? Reflect this image, the mirror itself onto the other side. Right? And that mirror also reflects 2 to 3. Right? This 3 is the image of 2. It's also the image of 1. By any chance, these 2, they are not overlapping, then they will do more images. Right? And we'll talk about that in a moment. Okay. So you want to take the image of the conductor itself. So this is the image of the left conductor with respect to the right. And then you keep repeating it. So there is an image here. This will have an image there. And it's probably not hard to imagine that this will be not this. So the next one. Right, am I doing this correct? So cross gets an image here. This gets an image here. And then you have positive and a cross. And it keeps going. And now the question I want to ask, most probably I haven't decided, is that now if you want to find the force on one of these charges, let's say this charge, this was the original charge, right? If I want to find the force on this, or the electric potential of this charge due to these two conducting plates, I remove the conducting plates and there is a series of charges. I have to find the electric potential with each one of them. So I forget this whole problem and I say that, oh, there's a charge here, a charge here, a charge here. It's like a crystal, right? Charge here, and so on. It keeps going. And I have to find the electric potential. This is going on. And I have to find the electric potential of this point due to everything else. Like this can interact with this can interact with this can interact. So interaction energy, let's say. Interaction energy will be, let me label them, right? So 1 prime, 2 prime, 3 prime, and so on. And this has to be 0 prime, and so on. Correct? So there is an energy between 1 and 1 prime, plus energy between 1 and 2 prime, 1 and 2, plus energy between 1 and 2 prime, plus so on, right? And it has to go to the opposite side also. That's only 1. And then you do energy of 2 with 1 prime, plus 2 with 2 is not allowed, right? 2 cannot interact with 2 itself, so you leave that alone. So you do 2 prime, plus energy of 2 with 3, and so on. That's equivalent to saying we are interested in energy between I and j, where I could run from minus infinity to plus infinity, and j could run from minus infinity to plus infinity, and I is not equal to j. Right? Each of this charge or images interact with another one, and we have to find the total of that. So that will be the interaction of this charge with these two conducting plates. And usually these are converging solutions, but it's not very obvious whether that summation can be done or not. Is that clear? And you can also find the forces, right? Forces are better with the sense they can cancel out even this as plus or minus. But the plus and minus, that sometimes if you have interchanging signs in a series, that means it's going to be converging very slowly, extremely slowly. Like if you have a series where they will all be 1 over r, right? They'll be smaller and smaller. But it will be nice if it is just all positive, because the next one will be smaller, smaller, smaller. But if it is interchanging signs, that means it will cancel away some of the whatever was that earlier. So these are called very slowly converging series. And one of the challenges is to get a number associated with that. For example, if you have a sodium chloride crystal, you actually have sodium chloride, sodium and a chlorine repeated. In a one-dimensional quantity, it is okay to calculate it, but if it is three-dimensional quantity, it is very hard to calculate that. Even today, I think this is called Madelung constant. Look up Madelung constant. So the energy associated with this is given in terms of a mathematical series, which is given the name Madelung constant. Might be off with the spelling. And I think recently, I think one of you guys mentioned that you are interested in finance, right? And one of my friend who was a colleague with me, he actually during his PhD made a significant contribution to this Madelung constant. Like the fastest way to calculate Madelung constant is by him. If you look up Madelung constant, that's his article that shows up. But he's not in physics anymore. That's unfortunate. No, this might be fortunate for the finance industry, but that's So it's that's something. And now let's do this for the actual homework problem. What if you have an angle with respect to each other? Right, so now let's say you have an angle formed. That's your, this is just for reference. And it was given that this is 60 degrees. Right? That's 60 degrees. Now we roughly get the picture of how to proceed, right? So we have a, let's say, we want to skew it, we don't want to keep it at the center because then it might just repeat itself and might not be a good example. And these are infinitely extended, right? So this should be thought of as exactly the same mirror that we were talking about. Earlier it was 90 degrees, now it is 120 degrees. Right? 60 plus 60, that's 120 degrees. The prescription we suggested was find the image of the mirror with respect to the other. Right? If this is your one of the mirrors, if I were to take a reflection of this, notice this should be thought of as extending backwards. This can extend backwards or extend it there. And now you reflect this. If this is 60 degrees, that's 60 degrees, that's also 60 degrees. So this will be your image. Right. That's right. That's your new. This is actually not really a physical image. Let me make it dotted if you want. Okay. This will have a reflection with the original piece, that's a negative charge. Okay. It will also, like this can also reflect with respect to this mirror, right? And where will that be? So this can reflect all the way here, right? It will go straight there. Notice it will be, again, I'm seeing it. So that's your image. So that's one image. So this is the image due to this mirror. This is the image due to this image. That's your two primary images if you want. This, if this was not there, that's the only image you will see. Correct? If this was not there, this will get reflected by this mirror, and that's all the way here. So that's all the way here if you want. If that makes sense. Is that clear what I mean by that? Try to gather that. Let me remove that so that we're going to have a lot of images. But now this is also a mirror, right? So this was reflected off this. Now this can get reflected from here. So this can also get reflected. That's your secondary image. So let's say each circle I can make this bigger and bigger. So this is the primary image. This is now getting the second. So this is the second image, like two reflections if you want. So that got reflected, and now this has been reflected off this. Now I can reflect this off in here. Right? So this is getting reflected here. So this will be positive. So that's negative. So that will be the next image. This is again project this backward, and that's the image coming from here. That's 90 degrees. Again, let me not put this line here. And this is now the third image, right? Third. If you want, right? Like this got reflected here, this got reflected with this, and now this is again getting reflected by the first one. So it's a third, three reflected. After three reflections, you will form this. So this will be significantly weaker And notice that this is in real space, right? If you started with two mirrors, you won't see this, right? But you will not actually keep your hand or something there, right? This is a real image. This was a virtual image in the sense that it's behind the region, so you have to be careful with what that is. And I think so it has to be real. Like where else can you see that? Or maybe it is inside, I don't know. Let me not say anything, let me not make it plain. We'll have to do the ray optics for really figuring out whether the rays are actually getting reflected or it's actually going through that point. Okay. That's your third. Now, but this one also can get reflected from here. So you can get the image here. And I think this is also the third one. Is that clear roughly? Okay. But then you would say I can keep doing this again and again. Okay. Now it turns out that if you choose your angles correctly, that's the only thing the museum people have to do that other than the quality of the mirror itself, that you have to really set this angle perfectly to 60. If you don't make the 60, if it is 61, this image, so next one will be forming the image on top of this. The fourth one will superimpose on this original source. But if you're off by even 60.2 or something, this will be slightly off, and then the images very quickly, this is going to get infinite reflection, right? Very quickly it will be off and it will be spread out. The image will not be a nice, simple, focused image. So you have to be really perfect at 60 degrees. That also lets you ask, and for what angles will you have this repetition? And you can show that whenever these are rational numbers, whenever these angles are rational numbers, then you can actually get, if not in the first iteration, eventual iterations that will come in. So if you have worked with rational numbers, I think one of you guys is working with integers, right? So whenever p, if you have two numbers p and q, if that ratio or if the ratio is consisting of prime numbers, then this repetition ends. And then if it's an irrational number, then you'll have infinite images, and then you can ask where those images are formed. Those are all nice exercises. And this whole thing was started, method of images, just to bring out the historical fact. 1848 by William Thomson. When he was just 24-year-old, and he is, we know him as Kelvin, right? Actually, Lord Kelvin. And a very nice exposure of this in the most of the modern literature. I feel this is not really highlighted very well, this whole concept of the strength of this, what you can do with this. What I suggest is go into the original, look up Maxwell's book. Maxwell wrote, I think he was supposed to write on electromagnetism, I suppose. No, maybe electricity and magnetism are other. So Maxwell's treatise on electricity and magnetism. Now, what's the page? I think, because I just today morning I was looking into this, I think it is page 275. It's a whole chapter associated with it. He begins by acknowledging William Thomson. They were friends. Maxwell, Tate, and Thomson. These three were really nice colleagues. All three did great work. And I think it is page 275, but it shouldn't be very hard to find. The whole chapter. Encourage you guys to just go over it. You don't have to read it. I'm not going to ask you questions from that. This is on your own if you really get curious. And it should be available in, what is it called? What's it? Archival. I haven't checked that, but most of the old books are available on Archival. I don't expect Maxwell's book to be still on copyright. I think it will be off from the copyright, so it should be available in here. So I think, I can actually ask, what is the force on this charge due to the two conductors, right? That means I have to find the force due to this, force due to this, force due to that, and add up all these things. So it seems a little work, but I think conceptually it's a very strong concept. And yeah, let me stop here. Thank you. Borden, was it clear? Any questions?
Yeah, I was trying to follow through everything you were explaining, like with all the diagrams.
Uh-huh. So maybe the video helps in these situations.
Yeah, probably.
Yeah. Try to read again or ask me again. And feel free to ask questions even related to the exam. So feel free to ask questions.
Yeah.
Like since it's a take home, I would say that, and you're allowed to use resources. So try to improve your grades for everyone. That's one way of looking at it.
Yeah.
An opportunity. Okay.
But yeah, sorry I wasn't able to come to class today.
No, that's fine. Yeah. Some advantages of having, sometimes you can take off. Good.
All right. Thank you. Have a good day.
You too. Bye-bye.
Thank you.